Hello, welcome back to our series of lectures. We have started off work, power, and energy. I think I did give you a definition of work the other day in my previous video. I want you to understand certain things broadly. Don't go narrowly with these bookish definitions. And when I made a statement like this, I meant that look, work, and heat are absolutely similar. And you have to understand this point very clearly because both are transient phenomena. Both are discrete functions. Both are inexact differentials. Both are transference of energies. If it is heat, transference of thermal energy, and if it is work, transference of mechanical energy. But remember, only during the transfer. When I am moving a body, as long as I am moving it only, work is set to be. Work is being done. We never say after performing work that something is actually stored in that. What will happen to the work? That's a very crucial question. If you perform so much of work, some efforts are going on, what is happening to all this? We will see that. We will see that shortly. What's going to happen to this work? Sometimes it is manifested in one form. Sometimes it is stored in another form. Let us see in how many ways this is possible. Okay? Right. Now, before that, I think I was about to talk about this conservative and non-conservative, very, very important concept. You see, in all the chapters of physics, you do come across open system, closed system, and isolated system. Any system that allows exchange of energy and matter. I think I was about to talk of this point. You take some water in a vessel without lid and try to heat it from below. You know that energy is being exchanged to the surroundings or the environment. And at the same time, you allow it to boil. I think with the form of vapor, the transfer also takes place. That's what we call as open system. Second is closed system. Closed system means what? Exchange of energy only. Here energy and matter both, but only energy. That means a vessel with certain liquid, put a lid on that, and then heat it. Through lid, of course, in the vessel, energy is going out or may come in, it depends. But that is what we call a closed system. And isolated, you have neither energy nor matter is exchanged. Thermos flask. There is surrounded with a band conductor of heat, and then you put the lid, so matter remains intact, energy remains intact, right? These are the systems that you should understand, okay? Now, yeah. So when I say from one system to other, this is the meaning, okay? All right. Now coming to the conservation. Now this is a very, very important concept as I was telling you. People say which force is conservative. You know, there are so many books and material which talk of so many things. They are honestly speaking not correct but not wrong also. But what we understand, this concept is from a totally different perspective. For example, if you have a an isolated system. Isolated system, that means nothing is allowed to go in, nothing is allowed to come out, either energy or matter. That's what I spoke to you a little while ago. Now, in this, there is an amount of energy present. Say, for example, the total energy is conserved. Now, total energy is conserved is not everything, but here I am talking of total mechanical energy if it is conserved. There are so many forces present inside. All are internal forces, whatever you have. If in an isolated system, if the total mechanical energy of this system is conserved, then the forces responsible for this are called conservative forces. I want you to understand. Forces which are responsible for conservation of energy are called conservative forces. I hope this is clear. And of course, all I am talking of internal here. Okay? Now, what do you mean by mechanical energy? Mechanical energy consists of kinetic energy, potential energy. If the sum, we call it as mechanical energy. If the sum is constant, then we say mechanical energy is conserved. In an isolated system, all the internal forces which are responsible for the conservation of mechanical energy are called conservative forces. What are the, first, this is how it begins. What are the examples of conservative forces? Conservative forces examples. And obviously this is non-conservative forces. Here, electrostatic force or Coulomb's force, gravitational force, gravitational force, light spring force. What do you mean by light spring force? If the spring's mass is negligible, then only we take spring force to be light. Then tension in light strings, chains, etc. That is also conservative. But you have to be very careful, okay? And then any central force, mathematically, this is a central force, this is a central force, all are central forces. But any central force, I am talking of mathematically. I'll come to that. So these are all conservative forces. Okay? What are non-conservative forces? One, kinetic friction. Two, viscous forces. Friction, viscosity, there is no difference. Viscosity is in fluids, friction is in solids, that's it. Then, heavy spring force. Tension in heavy strings. Alright? Now, obviously all non-central forces come under non-conservative forces. Now if I tell you, because although we can't say for certain, wherever the process involves conversion of thermal to mechanical or mechanical to thermal, mostly mechanical to thermal, their conservative forces are bound to be non-conservative because they do not allow mechanical energy to be conserved. They convert some of this form of energy that one possesses in a system into thermal energy. Never say the energy is converted to heat. You have to say the energy is converted to thermal form. Now this is important, okay? Mostly you will come across this. Many of you never come across these two in the textbooks. I'll tell you why this is non-conservative and why this is conservative. You take any spring, okay? Just take the spring. Now keep on pressing, press elongate, keep doing it 100, 150, 200 times you do it. Then touch this spring, it will be lukewarm. I don't say it's damn hot, but definitely that is a lukewarm case. Where has it come from? From within? From within? Or, I'll tell you one more thing. Have a smooth surface, complete smooth surface. Fix one end of the spring, attach a body, now pull and release. Now, if it is a conservative force, theoretically, it should keep on oscillating forever. And I am not introducing any kinetic friction on the surface. The only force acting on them are, of course, normal force. And normal force doesn't contribute to any of these things. And then gravity, we do not talk because both are balanced there. Now my worry is to look at what about spring force only. You elevate, definitely after 10 minutes, 15 minutes, half an hour, 1 hour, this will come to a stop. Where has this energy gone? Obviously, remember one thing, in most of the cases that you come across in nature, whenever you are missing that energy visibly, that is bound to be converted to thermal energy through cascading that. To the molecular level it always goes. Therefore, even when you talk of a spring, that spring force is non-conservative. Why? I tell you why. Because that spring, although we say is massless, it does indeed possess some mass. I am not talking of the mass attached to it. I am talking of the mass of the spring itself. And now, for example, if I neglect that, I mean, this is a theoretical perception. If I neglect that, what's going to happen? Suppose that some of the energy is lost and the temperature of this body for it to rise. I think this is out of context here, but still I can't help. The energy is bound to be utilized to raise the temperature of that spring. Mass is mass of the spring and S is the specific heat of the spring and delta T is rising temperature. This is present. This is present. But this is zero. So, no question of, when you take light stuff, no question of mechanical energy to be converted to thermal energy. Therefore, anytime you take a light string, etc., the force is conservative because mechanical energy is conservative. I hope you have understood this. And why did I say tension and heavy strain? You take a huge chain and attach a mass to it, leave it for some time, it's continuously pulling, or you may probably play with that and then try to touch it. That is going to be lukewarm. Same explanation as that of spring that I spoke about. No difference. Therefore, don't say that spring force is, because as far as heavy spring force is concerned, since some of the energy is bound to be lost, but we do not account for it. That is why they say spring force is a conservative force. Strictly speaking, not. Okay? Alright. Now, I have made another statement which is called central force. What is the meaning of a central? Anything can be central force. Your Coulomb's force is a central force, gravitational force is a central force, even spring force is a central force, etc. Mathematically, how do you write spring force? We know that, we write it. But this is actually not correct. You are neglecting it with this, but it will have certain other factors coming into picture, strictly speaking. Okay? But anyway, leave it. What do you mean by central force? A central force is one which is always directed away or towards the center, the so-called origin that you choose. Even it is always directed either towards the center or away from the center, along that line. It may be along this line, along this line, along any line. Either like this or like this. Right? Anyway you take it, then we say it is a central force. That is number one, first category. Second, that force magnitude should be function of position only. It is only position dependent. For example, here you will have one value, here you will have different value, all other factors are the same. And I bring it here, you will have different value, etc. But when I say position, now I take this body anywhere like this and bring it here. The value is not going to change. Because it's a function of position, no matter how it is brought to that position is the criteria. Therefore, when it is a function of position only, it's a function of position only, never depends on the path how it has come. Say for example, this is R1, this is R2. It may go from R1 to R2, it may go like this and come to R2, it may go like this and come to R2. The least bothered. Because that is the function of exclusive function of the position. Now this is very, very crucial. Okay? And theoretically only I can explain at this stage. Mathematically we can prove it, but that is beyond your scope. Maybe I will try to do it at a later date to show how this is going to be. Although I can't help going into a deeper mathematics that is probably not there at this stage, but you do come across that, I think, maybe in your next level, engineering or any other level, okay? So, conservative force I spoke about, non-conservative force I spoke about, So you have to be careful, and if it is in the direction of force, you will get one kind of work. If it is in the opposite direction of the force, you will get a different work, right? Now, with this background, now let me tell you, mathematically, follow me very, very carefully. I am talking of mathematically. How can you say a given force is conservative? Say, for example, if F is equal to Fc, suppose, I am saying if F is equal to Fc, then the curl of F, or rather I would say, if del cross Fc, or I would say F only, I don't say Fc, a curl of F. What do you mean by this? The del function, I dou by dou x, j dou by dou y, k dou by dou z, cross I fx plus j fy plus kfz. It of course gets into the so-called vector calculus, but bear with me for a while. When you have it, how do you work out it is nothing but the determinant of this, but remember, these are all mathematical operators. You are not multiplying anywhere. It's a convenient way to work out your, how do you get this? Let us say, first I, row column ignore. What do you mean by this? Dou y of fz. I am not multiplying here. In your usual cross product, you multiply. Now you take the operation. So how do you write? Dou fz, sorry, not here. Dou fz by dou y minus dou fy by dou z. Okay? Then minus, that is matrix rule. This one. Dou fz by dou x minus dou fx by dou z plus k dou fy by dou x minus even if you don't follow seriously, you still follow me, because it's going to be very, very useful. You will never get it out in your lifetime as to why this is given in all the books. This is this, that is that, etc. I'll tell you. Now, what did I say? If this is what we call as curl of f, all this. Now I am saying if this is 0, when the vector is 0, individually, every component must be 0. So let us put down dou fz by dou y minus dou fy. 0, dou fz by dou x minus dou fx by dou z is 0. Dou fy by dou x minus dou fx, dou y is equal to 0. So if your force function is given as a function of the position, it may be conservative force, it may be non-conservative force. So which is conservative, which is non-conservative, we will see now. And why this is so also I will discuss. First point we have seen, this is the condition for F to be Fc, conservative form. This is the condition that I am giving. Okay? Now you have got either or any, all you can prove, or if, depending on the function given, you may take only one and say that yes, this is conservative, etc. Okay, fine, there's no problem with regard to that. Now, when do you expect this to be true? If you want this to be true, I'm just giving, suppose Fz is plus or minus dou phi by dou x. Z, dou z. This is that. And Fx plus or minus dou phi by dou x Fy. What do you mean by this? If this is to be 0, this must be the case. Otherwise it can't be. Now look, dou phi by dou z, if you put it here, what do you get? I substituted dou by dou y of dou phi by dou z minus dou by dou z of dou phi by dou y. Partial derivative advantage is you may interchange the derivatives. It makes no difference. So these two are one and the same. In fact, you can write those 2 phi by dou y dou z, dou 2 phi by dou. Whether you perform with y first, z later, z first, y later, it's not going to make any difference. Remember, these two are one and the same. Therefore, this is bound to be 0. Same is the case with the next ones also. Now, see the analogy how I am coming about. First, I said, the condition for force to be conservative is that curl of F must be 0. Del cross F must be 0. The del cross F I have given. When will this be 0 if F is expressible as this? That means what? F bar is I dou phi by dou x, j dou phi by dou y, k dou phi by dou z. The whole thing is plus, the whole thing is not going to make any difference. Now, if F is equal to Fc, then del cross F is 0. So, del cross F is y, then Fc is bound to be, actually this is written as grade phi. It's a little beyond your understanding at this stage. But this one, okay? If you go in one dimension, I said plus or minus, then you write Fc is equal to mathematically, I am now telling you, repeating, mathematically, if you want to say that this is a conservative force, then that is always expressible as a derivative of certain scalar function. Always expressible. This is a mathematical rule I have just shown you. And if this is only negative, then phi is called potential energy. What do you mean by that? I'll come to this point again. I'm going to repeat this till you get it. If del cross F is 0, F is equal to Fc, and F is equal to grade phi, or F is equal to minus grade U. U is your potential energy. What do you mean by negative sign here? What do you mean by negative sign? Oh, that means if I write in one dimension, I said this is all FC. So one dimension, how do you write? Isn't it? Both are one and the same. Okay? Now I can rewrite this as F dot dr minus du. This is equal to minus of u2 minus u1. Okay? Or I write u2 is equal to u1 minus integral fc dot dr. I can write this in a different form. Delta U, change in potential energy, is nothing but this. This and this are one and the same. One follows the other. Okay? If U is given, you can get the force. If F is given, you can get the energy. But this negative sign is very crucial. Very, very crucial. This is work done. If this work done is against conservative forces, against conservative forces, the two internal conservative forces. Because I told you, it's all in the internal system only, system, closed, isolated system only, we talk about that. In such a case only this is true. In other words, what do you mean by doing work against something? Look at gravity. I am here, this is gravity force is like this. I am taking the body against the force of gravity. I am doing work against gravity. Therefore, I am able to, what could I do? I could store some energy in this. And if I release it, it will realize into kinetic energy. If air is absent, no viscosity, so potential is converted completely to kinetic energy. This is how you, what do you mean by potential? How do you understand this? The work done by internal conservative forces or the work done against, because of negative sign, against internal conservative forces is stored as potential energy. Now I am coming to answering a crucial question. What happens to the work done? This is what we were looking at. Now this work done here is stored. A spring, light spring. It is a body. I am compressing it. How is the spring force acting away? But how am I pushing it against the spring force? Therefore there is a storage. There is a storage. So when can you store energy from work done? Now, for example, you may say, everywhere this is true, why are you talking about this? You may get it out. Now I have got a rough surface, I take a body and keep on moving forward, backward, moving forward, backward. What's going to happen? After some time, you see, the whole thing is absolutely hard. You go against the kinetic friction here. Could you store anything? Nothing. What happened? What happened? All this energy is converted to thermal energy. And so once it is converted to thermal energy, it's a molecular randomness, it creates motion. There's nothing that we can do. And converse is not true. You can't get back thermal to mechanical just like that. There are lots of efforts one has to do. We're going to discuss, that's not a reversible process at all. It's not a reversible process. You can't get it. Unless you use some other agencies and other things. Very important point I am dealing with. You need to look at this point in a broader perspective. Okay? Now, what do you mean by this again? I am telling you, the work done against internal conservative forces in an isolated system is stored as potential energy. When you say potential, that means you can use it as and when it is required. Some storage mechanism is present. Wherever the complete storage is allowed, then those forces are conservative. And if you have a kinetic friction, non-conservative, I can't store anything. Mechanical form, I can't store. Thermal, if you want to use it in some other purpose, I have stored it, that is up to you. But as I said, that is not going to be in usable form. But potential energy is in usable form. Therefore, whenever forces are conservative, then only energy can be stored. Can I now recast this statement? In fact, potential energy is defined only when the forces are conservative. Only when the fields are conservative. Otherwise potential energy concept doesn't arise. That is number one. Number two, what are you defining here? You are defining change in potential energy. So, this can be positive, this can be negative. But if your reference, for example, U2 minus U1 is equal to, this is the thing. Suppose if U1 is 0, that is your reference level. Now you are aware, this is the ground. And this is the ground means suddenly we are on the top floor of a building. How can you say this is the ground? For me, that is the ground. When I am dropping a body, it will go and hit the floor, it will stop. But if you go on to the ground floor and then play with ground, the same thing you will say there also. So, for me, this potential energy is here. The person who is playing elsewhere, his potential. So, you are free to choose any level as a zero level. No problem at all. Suppose I am having here 0, it is 100, plus 100, plus 200. Suppose if I am choosing plus 100 as 0, then what will be plus 200? It will become plus 100. What will be 0? Minus 100. And suddenly you start asking, sir, how do you get potential energy to be negative? This is where I am cautioning you. Whatever we discuss is only a change, although colloquially we speak something else. And then what is the potential energy of this, you say? But you have to see that state and the previous state, and then only you say that is the difference. But the previous state, if I take it as 0, I myself call this as absolute potential energy, but it is impossible to work out absolute potential energy for any body. Very difficult. That is why potential energy is always defined for two body systems. Earth body, spring body, charge and the field. So you have, wherever it is, you look at the two body system and then talk. So now what do you mean by negative potential energy? The negativity is only because my reference is elsewhere. That is how you have to understand. Is that clear to you? Okay. So, now when do you define potential energy? I have come back to this statement on and off. If curl of force is 0, then F is called conservative, and then F is always expressible as gradient of any scalar. And then gradient means if it is a negative gradient, I call that as potential energy, and this is force. Suppose instead of force I take field, conservative field, then I will get here minus grade of potential, I say not potential, energy. If it is F, that is energy. If it is E, that is potential. You will know that when you go to gravitation or electrostatics about this point, okay? Is this point tricky now? Mathematically, we have arrived at the concept of potential energy. And the advantage of this is, look, here is a spring. I have placed a body like this, mass, and this is K. Now I have brought the body here. That is how it has been taken. Once it is here, it has certain potential energy. We will see what it is later on. But if I take it to this and bring it here, then only you get the same potential energy. If I compress it and then take it here, then also you will have the same potential energy. It is an exclusive function of the position. No matter how this position is arrived at, whether you drag it 1,000 times, once, twice, thrice, it makes no difference. That is what I spoke about in the case of your central force. This is also a central force. There only I can define potential energy. If you define potential energy, the force is bound to be conservative. So people now talk in different languages. I'm not talking of Hindi, Urdu, English, Telugu, etc. But if potential energy is there, is expressible, then your conservative force is defined as minus grade U likewise. But that's not the definition. I want you to understand this. Okay? Now, this is how it is. Similarly, take gravity. I am now taking this body from here till here. I will take up, bring it down. Take it below, bring it down. The value, once it comes to the same position, will not change. So this is crucial. So the position is important, the displacement is important. Therefore, whenever conservative force is used, then you can take displacement to get work. You take displacement to get F dot ds you can take. You get this point. This is very important. But if it is not conservative, you ask, sir, I have taken a body like this, 10 meters, and the force is, friction force is 100 newtons. 100 into 10, 1000, minus because against. So minus 1000 joules of work is. I bring back. When I am bringing back, frictional force is now opposite. Your displacement is forward. Again, the work done is minus 1000. What is the total work done? Minus 2000 joules. What is the displacement? 0. So if I take force and then multiply with the displacement, will I get work here? No. Because in this case, displacement is 0. So it is wrong to say that if displacement is 0, work done is 0. Well, if the body doesn't move at all, then the work done is 0. The body moves and displacement is 0, work done is not 0. But if it is gravity, now look, taking a body up, bringing it down. Total work done 0. Why? I tell you. I am taking against now. Maybe I have performed minus 100 joules of work. And when you bring it down, you will do plus 100 joules of work. So minus 100 plus 100, 0. Got the point? So the change while going up is negative, the change while coming down is positive. When you add the two, you are going to get zero. This is a very important one. Current differential while going negative, while coming also negative. Therefore, similarly, the work done there is non-zero in a round trip. And here, in the spring also the same thing. Spring also. What do you mean by that? Now, I'm going to explain, of course, about the spring in detail. As I said, this is your original thing. Now you have taken it. Once, you see, this is how spring force was acting, and this is your displacement when I brought it. So, negative energy. But once it is allowed to come to certain point, say original point, force displacement are in the same direction. And if it is 100, this is also 100, therefore 0. That is spring. I'll discuss spring potential energy separately in detail. But right now, I want you to understand this in a different perspective. Okay? Thank you.